This is a funny little topic where I try to cram as many of the techniques as you know as possible into one question. And in this question, the very first one we can work out, the very first technique we can use is Pythagoras to work out x. That's our first technique, is Pythagoras. So x squared plus 11 squared equals 12 squared. X squared equals 144 minus 121. X squared therefore equals 23. So x equals the square root of 23, which is 4.7958, etc. So that's your first technique. Now, the next technique I'm going to work out is, the next technique I'm going to use is SOHCAHTOA. I'm going to use SOHCAHTOA to work out this angle here, which I'll call alpha. So if that's alpha, that's the adjacent, that's the hypotenuse. So cos of alpha equals 11 over 12. So therefore alpha equals so that's 23.6, I think. Okay, so that's the use of SOHCAHTOA. What I'm now going to do is use Year 7 geometry to work out this angle here called beta, which is 180 minus 90 minus, which is 66.4. But it's actually 66.4435, etc., etc., because we don't want to use rounded answers in subsequent calculations. That was just using the fact that this, and this have to add up to 180. Okay. I'm now going to drop a perpendicular line here. And I'm going to use the half base times height area of a triangle. But I don't actually know this, so I'm going to call that h. And so half the base times the height equals area of the whole triangle. Okay, so that's me using that technique. I'm now going to work out the area of the triangle again. Now I'm always telling people to draw out triangles separately if things are getting complicated. So I'm going to practice what I preach. And we'll work out the area of this triangle again using the alpha, which is 23.5565, and this side, which is 11, and this side, which is 12. Now, the formula I'm going to use for area of triangle is half AB sine C. So that's, I'm going to call this capital C, this little c, this little a, this capital A, this little b, and this capital B. So the area is equal to half 11 times 12 times sine 23.5565, etc. Remember, the dot dots are to remind me to use that in all its gory accuracy. That doesn't mean typing it in again, it can mean using the answer button. Okay, so when I do that, I get an area of 26.4. Now here's the thing. Two different ways to work out the same thing must give the same answer. This is my next thing that I'm using. This is a problem solving principle. So, therefore, this was my half base times height method. This was my trigonometry method. They're both working out the same area of the same triangle, so therefore I can stick an equal sign in between them. And I can simplify that. And therefore H equals, I think 4.4, but that's only rounded. It's actually 4.396179, etc. Okay. Now, as you might know from other videos, I'm a big fan of updating the diagram. So we've got this is 4.39, etc. This angle beta was 66.44, etc. This angle alpha 1.556, etc. Okay, so what have I used so far? I've used Pythagoras, I've used SOHCAHTOA, I've used Year 7 geometry, I've used half base times height, I've used half AB sine C, and I've used two different ways to work out the same thing must give the same answer. But that's not all. What I'm now going to work out is this stretch across here. Now, here's the thing. This is a right angle, so that is beta. This has to be alpha as well. Why do I know that? Because beta and alpha are both angles in the same right angle triangle, whether it's the big one, so there's the beta and there's the alpha, or it's the small one, there's the beta and there's the alpha. Same with this triangle here as well. There's a right angle, there's an alpha, so that must be a beta. This makes sense because, check it out, we've got a 24 degrees there and a 66 degrees there. They go together as a complementary pair in the same right angle triangle. That means that this triangle and this triangle are similar because they have the same angles. And if they're similar, that means we can use the fact that these triangles are in the topic, where if you double one thing, you double the other. So, I'm going to draw these triangles out very, very carefully. This is the little triangle on the left. Just going to use the alpha and the beta because they're a bit neater to write than the decimals. And then we have the large triangle, which is this. And this now was the beta, and this was the alpha. Now, that was an 11. That was a root 23. And that was a 12. And that was a root 23, of course, as well. And this was a... we discovered that as the height. That is a 4.39, etc. Now, in order to use the similarity, I'm going to reorient this larger triangle. So here's the smaller one again.
So he's saying maybe it's something we can sort out over the phone.
And here's the larger one turned around so that the longest side is on the right. So the longest of the two non-hypotenuses is 11. The hypotenuse was a 12, and that shorter side was 23. And remember, I'm trying to find this. So let's finally use the topic where if you double one thing, you double the other. How does a 12 become a root 23? Well, go via the number 1. So first divide by 12, and then times by the square root of 23. And the whole point of similarity is that you can use that on the root 23 to become the y. So if you take root 23 and you divide by 12 and you times by root 23, you will get the answer for y, which is and there we go. So we've used Pythagoras to start, then we used SOHCAHTOA, then we used Year 7 geometry, then half base times height, then half b sine c, then two different ways to work out the same thing must give the same answer, and finally we used similarity. Let's do another example. Okay, so first let's do one of the two basic things. Let's let's call this x and this y. Okay, so let's say that so this is using SOHCAHTOA. Let's say sine 30 equals the opposite over the hypotenuse, and therefore y equals 5. Now, so that's my SOHCAHTOA out of the way. Now I'm going to use Pythagoras. That's 5 there now. So therefore, x squared plus 5 squared equals 10 squared. X squared plus 25 equals 100. So x squared equals 75. So x equals the square root of 75. So that's now that. Okay, I'm now going to work out the area of the triangle using half the base times the height. You can always orient the triangle however you want. So half the base is half of 5 times the height, which is root 75. So, oh, I just forgot, I'm going to use Year 7 geometry now to work out that that's 60. So let's call that alpha, that beta. So alpha plus beta plus 90 equals 180. So therefore beta must equal 60. So we've done Pythagoras, SOHCAHTOA, Year 7 geometry. I'm now going to do half base times height. I'm going to turn the triangle around. This is the base, this is the height. So half the base is half times 5, and the height is root 75. and that is 2.5 times root 75. Okay, I'm now going to use area of the triangle again. This time I'm going to use half AB sine C. So that's a 10, that's a 5, and that's a 60. So let's call that capital C, that little c. Capital B, that little b. Capital A, little a. So the area equals half A B sine C, which is 21.7, but I don't want to use rounded answers in subsequent calculations, so I'm going to write it in all its gory detail, 21.6506, etc. Okay, so that's the area of the triangle. We've now used half base times height and half AB sine C. Okay, now I'm now going to use the principle that two different ways to work out the same thing must give the same answer. So we worked out the area of a triangle once, we got this. We worked out the area of a triangle again, we got this. And so therefore, oh wait on.
He was a librarian. Or where's the Boston? He is a librarian in Cambridge.
I thought I was trying to work out something here, and
I want to buy one, you know, because he's
I'm clearly not, because that is the same as that. What I meant to do was what I did in the other example.
So where it's just a ruin and the
I'm going to work out this.
haven't kept the land, or you know, things like that. So it was
So half the base times the height. Half the base is 5. The height is h. So that's one version of the area of the triangle. Here's another version. So divide both sides by 5. You get that. So therefore h is 4.3301, etc. Does that look roughly right? That's a little bit less than the square root of 81, so this is a little bit less than 9. Half of something that's a little bit less than 9 would be a little bit less than 4.5. Okay, so we'll now use two different ways to work out the same thing. We worked out the area of the triangle twice, and we stuck an equal sign in between. This was me sticking an equal sign in between two things I already knew. That's not very useful. This was me sticking an equal sign in between two things, one of which I knew and one of which I didn't. That's very useful because you get an equation that you can then solve. So what I've just done is found the h, and that's 4.3301, etc. Okay, finally, I'm going to work out this distance here. I'm going to call that w. Now I'm going to be very careful here. I'm going to use similarity. I'm going to copy these two triangles out. Now remember, if that's beta, that has to be alpha because alpha and beta are in the same triangle. If that's alpha, same right angle triangle. If that's alpha, that has to be beta. The reason why I'm marking them in is to help me keep track of my triangles when I draw them out. This is the smaller triangle on the left. It has an alpha at the top and a beta at the bottom. It's got a 5 there, a W there, and a 4.3301. Now I'm going to draw out the bigger triangle. Okay, that has got a root 75 there, a 10 all the way across there, and a 5 there. I'm now going to reorient this triangle. I'm going to draw it so the alpha, remember this was the alpha and this was the beta. I'm going to draw it so the alpha is at the top. The alpha is at the top, the 5 is on the other side. The longest side is the 10, and this non-hypotenuse longer side is root 75. So now let's use similarity. I see a 10 becoming a 5, that's halving. So therefore, a 5 becoming a W must also be halving. So therefore, W equals 2.5. And that's me using similarity.